Alright, hi everybody. We are back with another Stata tutorial. This time we're going to look at the theory and application of a simple co-integration model and how to do a couple different ways in Stata. So the general background, when two or more variables are co-integrated, it means they are individually non-stationary, but a linear combination of those variables is stationary. And the reason why this is going to be so useful is we can interpret that linear combination as a long-run, steady-state equilibrium level, right? So when we have deviations from that level, we can use that to predict future corrections, hence the error correction model that takes advantage of a co-integrating relationship. So the example we're going to look at today, you can see we have a pretty sparse little data set here. We're going to look at the question of whether or not one individual asset, in this case Bank of America stock, is co-integrated with the market movements in general. So it's going to be a co-integrating error correction extension to a basic capital asset pricing model. Can we predict an individual asset's changes using the market as a whole? So if you want to see where this data came from, it came from Yahoo Finance, right? So I've got a previous video on how to download the data, how to turn it into a Stata file, how to generate some of the basic variables. So what we've got here is the price, the level of Bank of America stock, and then the level of the S&P. And the first step we need to do is to create our returns, right? So let's generate a new variable, call it RBAC, and that'll just be the difference, and this is daily data, so the daily return from one period to the next, the difference in the price, PBAC, relative to the lagged value, so L dot price underscore BAC. So there's our asset return, and then we do the same thing for the level of the S&P. So what we'll call our new variable RSP, so the S&P 500 return, the change from one day to the next, divided by the one period lag value. So D dot SP over L dot SP. So those are going to be the variables of interest, the levels and the differences, or the levels and the returns. And then our program here, our steps to test for and take advantage of co-integration are going to be pretty straightforward. Right? So step number one is to do our kind of standard Dickey-Fuller unit root test on the levels and differences, or in this case the levels and the returns for both of our variables. So we want to verify that both variables are integrated of order 1, right? So meaning non-stationary in levels but stationary in differences. Step number 2, we estimate the co-integrating equation. So this is going to be that linear combination of our typically non-stationary variables. Then once we have this linear combination, the most important step, we need to verify that that linear combination is itself stationary. It acts as a long-run kind of point of attraction over time. So we'll use essentially the Dickey-Fuller unit root test again, but with adjusted critical values, the so-called Engle-Granger critical values. And then lastly, once we have that co-integrating relationship established, we take advantage of it with this error correction model. We see if we can get a little boost, a little extra forecasting or predictive power out of that equilibrium relationship. All right, so let's get back to the data and take a look. So step number 1, let's use the Dickey-Fuller unit root test on the price level of our stock, our BAC. And I'm going to do it here without including a drift or a trend term. You generally want to verify your results by looking for robustness to specification. Here we'll just do the default Dickey-Fuller test. And we see we do not reject the null of a unit root, so check box number 1, the price level is non-stationary. Then we do the same thing on the difference and kind of playing the role of the difference is going to be the return here. But it'll turn out the same either way. So let's apply the Dickey-Fuller test to the return on our stock, BAC, RBAC. And here we can strongly reject the null of a unit root. So non-stationary in levels, stationary in differences. Our asset is I1. Then we verify the same thing for the other variable, in this case our S&P. So Dickey-Fuller test on the level of the S&P. Do not reject the null of a unit root, so we get our Dickey-Fuller test statistic does not surpass any of the critical values at 10, 5, or 1% in absolute terms. So non-stationary in levels. Apply the Dickey-Fuller test now to the return on the S&P, and we here again can strongly reject the null. So same thing, non-stationary in level, stationary in difference or return, so it also is I1. So that's the first critical step. Our variables have to share the same order of integration and they have to be non-stationary. So now, step number 2, we estimate just a super simple linear relationship with the regress command. We regress our price level, the RBAC, as a function of the level of the S&P. And this estimated coefficient here, this is what we would call our co-integrating parameter. Right? That's what gives us the linear combination. Right? So playing the role of that linear combination is going to be the residuals from this regression. Right? So we'll use our post-estimation command, predict, a new variable, call it S, that's going to be these residuals. Now let's take a look at what we just did here. So these residuals, right, this is the level of the price of our asset, Bank America, as it deviates from its predicted percentage, its predicted value relative to the S&P. So when we see like a case like this, where we have a series of positive values, well, that tells you our asset price is above its predicted level. It's above its equilibrium. So we would predict a correction. All these values here where we have these negative levels, well, our price of Bank America is less than that which would be predicted relative to the S&P. So again, we would predict a correction here. Quite a correction occurs. So that's what we want to take advantage of in that last error correction step. But before we can do that, we need to verify stationarity of this linear combination. So let's again apply the Dickey-Fuller test in Stata to this linear combination S. And here, I'm going to include the option no constant in that test. So we're assuming no drift, no trend, no constant. And we get our test statistic here of negative 3.204, and it surpasses each of these critical values. So we want to say, aha, we have stationarity, but we have to remember these are not the right critical values, right? These are the Dickey-Fuller critical values, but because we are testing an estimated value, we actually have to have larger critical values. So we have to go to our Econometrics textbook or Google Engle-Granger Cointegration critical values, and you'll get something that looks like this. Sorry. So this is from the Engle and Yu 1987 paper, where they had a variety of tables of estimated critical values for exactly this scenario. So our case has 252 observations, so the closest we're going to get here is a sample size of 200 with 2 variables in our co-integrating system, and our 1% critical value, 4.0, well, we didn't surpass that. 5% critical value, 3.37, didn't surpass that. 10% critical value, 3.02, we did get past that. We had that 3.2 test statistic, so we have co-integration at least 90% confidence. So that's enough for us to proceed. So let's jump back into Stata. So there's our test statistic. greater than that 10% critical value. And now finally we can estimate a error correction version of a capital asset pricing model. So now our dependent variable is going to be the return. On the right hand side we'll put the S&P return, and then we'll add in this value, the lag of this linear combination, L dot S. So again, remember what that means. A large positive value of that linear combination yesterday means we were above our predicted value, and we'd predict a correction today. When it was negative, we'd expect it to come up today. Right? So we expect to see a negative and significant coefficient, and right on cue, that's what we get. So the coefficient here, this negative 0.002, significant at beyond 1%, beyond 99% confidence, tells us just that we have this correction towards long-run equilibrium. So we could use that as our superior prediction model over and above just a simple time series CAPM. Okay. Now, I did want to add one more thing here. So obviously there's lots of things you can do here in terms of how to incorporate that error correction model, how to get alternative specifications here. We could test for an ARMA structure predicting these returns. That's all on the table. But all of these steps for testing for cointegration can be combined into a built-in Stata command. And this is one of those cases where you're going to have to download the do file, essentially, to run the command. So you're going to have to type in ssc install Engle-Granger. And I already have it installed, and it should tell me that. But once you have that installed, you'll be able to run this command that has quite a few different options. But the most basic is if we just type in Engle-Granger and then list the variables that we want to put in our co-integrating system, in this case our asset price, BAC, and our S&P level. Okay. And look what it does. It gives us the test statistic for the linear combination, for testing the stationarity of that S, residual linear combination. So it estimated the linear combination for us, it estimated the co-integrating equation, saved the residuals, and tested it. And most importantly, it tested with the correct critical values. Right? So these are a little bit different than we had in the table because these are actually exact critical values for our 251 observations. So here we see our exactly the same coefficient test statistic that we estimated, and again it is 10% significant, not significant at 5%. So that could have saved us a little bit of time. Always nice to verify you know what these commands are doing. There are some other options here where it'll run kind of a default version of an error correction model. I generally prefer to do that part myself. Once you've verified stationarity here, you can go ahead and include it in the model as you see fit. So, as always, hope you found it interesting. Put any questions you have in the comments, and we'll see you next time. Thank you.